This is the introductory video for learning about the material in Chapter 1. Before this point, you should have watched one video where it was an introduction for the entire course, just what are differential equations. In this video, I'm going to talk about what to expect in Chapter 1 and try to motivate you to want to study Chapter 1. Because I think that's going to be a big part of your success in this course, is can you motivate yourself to study without having a professor there reminding you to study. You're going to have to go to these videos and read emails or look at things on Blackboard, on the web, to see and get motivation to study and keep on top of things. So let's take a look at this PowerPoint. So this is a Chapter 1 overview. What are we going to do in Chapter 1? Well, the main focus of Chapter 1 is on what are called scalar differential equations, one scalar differential equation, rather, or as opposed to systems of more than one scalar equation or vector equations, which is the main topics of Chapters 2 and beyond. And one of the main kinds of models that we're going to consider in Chapter 1 are population models. Actually, we do consider systems a little bit, and especially in the very first section, which I'll be talking about in another video. But in this one, I want to focus on population models that are scalar, one-equation models. We'll start with the exponential growth model. That's the simplest kind of population model that's still relatively realistic. Something that would be not realistic would be like a constant function or something like that. When you create mathematical models, the first thing you want to do is you want to identify your variables and any parameters. In this case, we've got two variables. T is time. You'd want to give units. I am specifically not giving units here in this talk, but in general, when you're doing homework problems, you want to give units. Could be years, could be months, could be days. If it's bacteria, it could be hours, or even minutes. The dependent variable is the population. If it's people in a country, it might be in millions. If it's, say, predators in a certain region, it might be hundreds. There are lots of different things that could be. P sub 0, or you might say P naught for short, is a fixed number. That's your initial population at time equals 0. That, in a sense, is a parameter. Now, what is a parameter? You see the next thing labeled as a parameter, k, the growth rate constant. Parameters are constants when we're trying to think about one particular model and for a particular situation. However, and this is really key, what we usually do with parameters, and in fact the most interesting thing to think about with parameters, is to ask what happens as we let parameters change. So it's like we're letting a constant change. We don't use the word variable, we don't use the word constant, we use the word parameter to sort of have a halfway between point in a sense. They're constants, but we like to think about what happens as they change. Actually, the word parameter has other uses in math, and in fact we'll use the word parameter in other ways in this course. Sometimes we'll think of t as being a parameter. When you talk about what are called parametric equations and the graphs that they create called parametric curves, that's another use of the word parameter, and it really means something slightly different than the way I'm using it here. Here's the model. It's a differential equation. dp dt equals k times p, where k is a positive constant, this parameter that's called the growth rate constant. It's a differential equation because it involves a derivative. The derivative of p with respect to t. P is an unknown function. And when you write the model, when you write this equation, you're trying to think about how the derivative can be described in a way. You might start off by saying that the rate of change of the population is proportional to the population itself. Okay? The more bacteria you have, the faster the population is going to grow, because there's more bacteria to reproduce. Same with other kinds of things. You want to keep it simple. While you could put a p squared or a p cubed here, Keeping it a p to the first power is keeping it simple. That's what you would like to do. K is the constant of proportionality. We don't want to assume that k is 1, for example. That would be inflexible. Putting the k in there gives us a little bit of flexibility. We add this condition. This is function notation over here. It's not p times 0, it's p of 0. P is a function of t. And so sometimes, well, let's see, where did my black marker go? Sorry about the camera is so squeaky. It's usually not quite that squeaky. Here's a blue marker. Sometimes you'll see people write this. Why don't you zoom in on that? I don't know how well it'll show up. I thought I had a black one. Oh, here, let's see. Here we go. Sometimes you'll see teachers, especially in science courses rather than math courses, but this particular math course is maybe in some ways a little bit more like a science course than most math courses. You'll see people write that kind of thing. Technically speaking, that's called abuse of notation. P is standing for two things, both the dependent variable and the function name. Okay? What's the message here? If that bothers you, get over it, okay? It's what's traditionally done. Don't make a big deal out of it. Most scientists don't. Dependent variable and function name. Sometimes we'll write the dependence on t explicitly. Sometimes we won't bother with that. Okay? You just have to get used to it. So when you see this is p of 0 equals p naught. The population at time 0 equals this particular number. Now this particular function that you see down here, and here I'm using notation. This particular function that you see here, p naught times e to the kt, you might want to zoom in on that if it's not real clear, is a solution to the differential equation. How do you check that it's a solution? It's pretty simple. Believe it or not, lots of people have trouble on this point. Okay? It's pretty simple. All you have to do is plug this function into the left-hand side of the equation and simplify. Then on another line, plug it into the right-hand side of the differential equation and then simplify. And see if the simplified expression as a function of t is the same in both cases. Let me do it quickly on the board here. LHS stands for the left-hand side of the differential equation. That's dp dt. For that particular function, p0 times e to the kt, remembering that I'm differentiating with respect to t, I get an extra k from the chain rule when I take that derivative. On the other hand, the right-hand side of the differential equation is k times p. When I substitute this function into this equation, replace the p with p naught e to the kt, lo and behold, I do get the same. I get the same function. It doesn't matter what k is. It doesn't matter what p0 is. Those are the same thing for all values of t. Those are the same functions. Okay, so this is a pretty easy thing to do typically, is to check to see whether this function is a solution. You can check that other functions are not solutions just very quickly. For example, p equals t squared is not going to be a solution. Why? The left-hand side is the derivative. That's 2t. The right-hand side is k times the function, k times p. This function is t squared. I get kt squared. Kt squared. And while these could be the same at certain values of t, like t equals 0, they're not the same function. Not the same. The point being that that function, t squared, is not a solution to the differential equation. All right? So you've probably seen this in pre-calculus courses before. Exponential growth is what happens. The graph looks like this. It's an exponential growth curve At t equals 0, you get a value of p sub 0, which in this particular graph happens to be 1. And as t increases, it grows faster and faster. The graph is concave up. The slope is getting faster, higher and higher. The rate of growth is getting larger and larger. It's pretty realistic in certain situations, but it's not realistic in the whole. If you keep letting t get bigger and bigger, this grows faster and faster without bound quite quickly. Is there something that's more realistic? The next step in realism is something called the logistic model. By the way, these first two models are going to be something that you read about in the very first section. So in a way, this is kind of a lecture on section 1.1 also. Instead of assuming you got exponential growth forever and ever, assume there's some kind of limit on growth. Call it n. Think of n as a limit that if you start with a small population, that small population, when it grows, it can't get above n. It's got to level off before it gets to n. On the other hand, you might also assume that if your population for some reason starts off higher than n, that those bacteria or whatever are going to die off faster than they grow, and the population is actually going to decrease to n. That's called the logistic model. We assume exponential growth when p is small. And we also assume the fact that we want p to decrease when p is bigger than n. And you'll read in the book a derivation of why this was going to satisfy those assumptions, this equation right here. Let's just very quickly think about it right now. If p is small, okay, think this kind of intuitive thinking that I'm going to do for you right now, heuristic thinking, is something that you want to get used to. If p is small, then p over n is pretty small, close to 0. 1 minus that is close to 1. Basically, this term right here is close to 1. In other words, the right-hand side of your differential equation is close to k times p times 1, or just kp. It's acting like an exponential growth model. On the other hand, if p is bigger than n, those are positive, but this is negative. Think about it. Imagine p is n plus 1. n plus 1 over n is bigger than 1. 1 minus something bigger than 1 is negative. This becomes negative, meaning the derivative of the solutions are negative, and so the solutions are decreasing. And in fact, when p is close to n, this will be close to 0, meaning your derivative is close to 0, and your graph is close to horizontal. In fact, when p equals n exactly, if you start off with a value of n, and is sometimes called the carrying capacity, if you start off at that population, that's exactly 0. dp dt then is 0 initially, and in fact will stay 0 all the time. You'll get a constant function at p equals n being a solution. Doesn't mean that in reality there couldn't be some fluctuations, but as far as the model goes, you get a constant solution, and you would predict a close to stable population in reality. We still have an initial condition that's the same as before. This equation is more complicated. You should expect a more complicated formula. Zoom in on that formula for the solution. This formula can be found by techniques you will learn in section 1.2. You can see it's pretty complicated. What you need is something called separation of variables and some integration and some algebra to get it. For the moment, we'll just look at it and think about it very briefly. It's more complicated because it's a more complicated differential equation. I won't bother to check that it solves the equation. I could. I'd differentiate it. I'd plug it in on the left-hand side, differentiate it, simplify. Plugging it on the right-hand side, I'd do some algebra to simplify it, and lo and behold, if you do it all right, you would get the same thing at the end. Maybe you want to even check that right now. Pause the video and check that on your own. The algebra is fairly nasty, though. It's good practice. Does it satisfy what we would want it to satisfy? For example, is this initial condition satisfied? Plug in t equals 0. E to the 0 is 1. On the bottom, you get, therefore, p0 plus n minus p0. The p0's cancel, leaving you with just an n. And that n divides out with the n on the top, leaving you with just p0. So it satisfies that initial condition. Think about that if that went by too fast. Write it on a piece of paper. It also satisfies the condition that if, if as t goes to infinity, if p0 is positive, this is going to approach n. Why? As t goes to infinity, e to a negative kt, that goes towards 0. This term here gets very, very small, meaning this whole thing goes towards 0. In the limit, you replace that with a 0, you've got a p0 just by itself on the bottom, that divides out with p0 on the top, and you're left with an n. Here's what the graphs of some solutions look like. In this case, I picked k equal to 1 and n equal to 1 also. You can see a horizontal asymptote for these two solutions at n equals 1. Those are a couple of different solutions for different initial conditions. Differential equations, in general, have infinitely many solutions, though if you specify an initial condition, it will, in general, have one unique solution. Is that realistic? Well, yeah, it's more realistic. What about if you got harvesting, like fishing, for keeping track of fish populations and people who are going fishing? You might try to bring in the effect of fishing, like subtracting c, a constant from the right-hand side, to model a constant rate of fishing over time. The equation becomes more complicated. In fact, the solution can be found by integrating. It actually can be found straight away through integration. However, integrating this may be more trouble than it's worth. If you spend a few minutes thinking about it, once you learn about section 1.2 and separation of variables, you'll realize that, especially because we have just arbitrary constants here, these parameters k, n, and c, that you've got to think about cases, because you end up with a quadratic function in a denominator that you're trying to integrate. And it depends on whether it's got real roots or not. In certain cases, you might have to use partial fractions as your technique. In other cases, you'll need to use probably some substitution combined with the fact that the general antiderivative of 1 over 1 plus x squared is the arctangent of x plus c. Believe it or not, that fact is important in those cases when you don't have any real solutions to the quadratic that was in that denominator. So the point here is that solving this is more trouble than it's worth. So do we give up? Does that mean we don't think about equations like this? Do we not think about hard equations? No, we don't give up. What we do instead is we change our methods. To the rescue, numerical and qualitative techniques. Now I'm going to teach you a little about numerical techniques, mostly focusing on something called Euler's method, because Euler's method is the most intuitive technique. There are certainly better methods than Euler's method, as far as being more accurate. But you need to learn a little bit. Euler's method is what you'll learn about. But mostly I'm going to focus on the other idea, qualitative techniques. And basically, qualitative techniques means you're thinking about what graphs should look like without actually necessarily knowing precisely what they look like. And maybe because you've got parameters in the equations, and therefore you can't know precisely what points they go through sometimes. So we'll think about the graph on the right-hand side of the differential equation, abbreviated diffeq. We'll think about some things called slope fields, phase lines, and the most sophisticated thing is to think about something called the bifurcation diagram. Right now, I'm going to very briefly introduce you to these ideas. This will make more sense as you continue working through chapter 1. Well, here's a couple slope fields first. That's the exponential growth model. What you see here are a bunch of vectors made with Mathematica. Actually, you shouldn't necessarily think of them as vectors. Just think of them as line segments that are essentially plotted using the differential equation. In the exponential growth model, again, that was dp dt equals k times p. If I'm going to make a plot, I do need a value of k. I think I made this one with k equals 1. And basically every point in this plane, let's focus back here, has coordinates, t and p coordinates. Take this one right here. That's close to the point, not exactly, but close. Well, it looks like t equals 0.8 and p equals 5. Okay? So the coordinates of that are 0.8, comma 5. The p coordinate in particular is 5. You draw this line segment at this point in such a way, or Mathematica is doing this, in such a way that it's essentially taking that point, and in this case just the p coordinate of the point, 5, and plugging into the right-hand side of the differential equation. Zoom back over here. To get a 5 over here and saying, hey, that equals the derivative of my solution function when it passes through that point. In other words, the slope of that thing is the slope of my solution curve. Let's come back over here. This line segment has a slope of 5. Now, it doesn't look like that, but in fact it does. The horizontal displacement is 1 from 0.8 to 1.8, and the vertical displacement is 5. 5 from 5 to 10. 5 over 1 is 5. The slope of this is 5. The slopes of these are bigger because p is bigger when I plug into the right-hand side of the differential equation. And notice the solution curve is kind of following this slope field. One thing to be careful of here, though, is when you read about slope fields in section 1.3, Mathematica is drawing these so that it's getting the correct slope at the left-hand side of the line segment. The book talks about making these marks so that the slope is correct at the midpoint. Okay? As long as you know which one you're doing, it's okay either way. Here's the slope field for the logistic one. Again, you can see how the solution curves follow the slope marks. Every time a solution curve passes through the base of one of these line segments, it's going to have the same slope as the line segment does. And in this way, you can get computers to draw this for you. In this way, you can predict what the shape of solution curves are going to look like, even without finding formulas for them. So as long as you got that technology, that's pretty nice. That's pretty easy to do. But what about if you don't have that technology? Or what if you don't, what if you do have it, but you'd like another way to think about it? That's where you're going to get into what are called phase lines and bifurcation diagrams. Focus on the middle here. Let's see. It's like we don't have a black screen option on this. I should have checked this ahead of time. It looks like maybe not. Let's move the overhead projector over here on the right. Here's one. You'll see in future videos that I continue to have some technical difficulties sometimes getting things to look nice for you. We'll do the best we can here. Let's go back to this harvesting model. dp dt equals kp 1 minus p over n minus c. Okay? You're not going to understand fully what I'm talking about here, what I'm about to say, but that's okay. Okay? You can come back and view this video again if you need to. But what I'm about to say is really important, a really important perspective that you want to get out of this course. First thing I would do to think about this qualitatively, instead of making the slope field, is I would think of this thing on the right-hand side as a function of p, f of p. Can you see that big enough? Is it coming out? And think about what the graph of that function would look like. Really, if you're going to think about what the graph of that function is going to look like, you should label the horizontal axis now with a p. Before, we labeled the vertical axis with a p when we were drawing the solution curves. Since I'm thinking about the right-hand side as a function of p, and since we traditionally put independent variables for functions on horizontal axes, that's what I'm going to do here. But that's a point of confusion for people, but don't let that confuse you. Work on that. The vertical axis I could label with whatever I want, but actually I'm going to label it with a dp dt because that's the left-hand side of the differential equation. What does the graph of this look like? I don't know exactly, because I don't know k, n, and c. However, there are still some features that I can draw. For example, this is going to be a parabola. This is a quadratic function in p. I can multiply this out, get a kp minus k over n p squared, then minus c. It's a quadratic function in p, and what else I know about it is the coefficient of the p squared is negative k over n. That's negative, since k and n themselves are both positive. So the graph is going to be a parabola that opens downward. If c happened to be 0, let's just pretend that for the case, for the moment, I would also know the roots. If c were 0, this term would be gone. The roots would be p equals 0 and p equals n. Think about that for a second. P equals 0 and p equals n are going to be the roots when p equals 0. So I could draw a picture like this. That's the graph of the right-hand side when c equals 0. I want to relate this graph to the graph of solution curves in that old plane that I have on the screen, the TP plane. Now I want to put n on the vertical axis. In that case where c is 0, I already looked at the graph of a couple of solutions. You've got some solutions that are going up and some that are going down. It depends on if p is bigger than or less than n. That's reflected in this graph. When p is between 0 and n, dp dt, the second coordinate of these points, is positive. That's telling you solution curves are increasing for conditions where p is between 0 and n. If, on the other hand, p is bigger than n, this graph is below the axis. So your solution curves are decreasing when p is bigger than n. What's most interesting, though, I know I'm running low on the time I wanted to give this to you. Let me just very quickly summarize what's going to happen. What's most interesting is trying to figure out what happens as c increases. As c increases, since I'm subtracting it, this graph is going to shift downwards. I'm not drawing this very well, but eventually there's going to be some value of c where this just barely touches the horizontal axis, and then for all bigger values of c, it's going to be below the axis. What that's telling you is that if c gets too large, if the harvesting of those fish is too large, dp dt is always going to be negative. And your solution curves will always be decreasing down to 0. A bifurcation has occurred. Come back to this screen. And over here, a bifurcation, a big change has occurred in the qualitative nature of the solutions. No longer do you have these two constant solutions at 0 and n, and solutions increasing in between them, but all of a sudden, all solutions are decreasing. That would be bad for the fish, by the way. Of course, it's not a perfectly accurate model, so you can't take that too far. It's more of a metaphor of what perhaps could happen than a guarantee that something will definitely happen. This is a particular program that comes with the CD-ROM with your book. It's called phase lines. And basically the equation down in the lower right here, you might want to zoom in on that quick, is essentially the differential equation we were looking at, though the k is 1 and the n is 1. This is an a here, if you can't quite see that. This says dy dt equals y times 1 minus y minus a. A is like the c. It's the parameter that's the harvesting. The slider up here allows me to change the value of a, to increase it from 0 to up to 0.5. Zoom back out a little bit. What you see in the rest of this are a bunch of things. In particular, this right here is a graph of the slope field, along with a red and green line at the constant functions, which are solutions, 0 and n. And watch what happens to that picture now as I increase a. So focus on the picture in the top middle. I'm increasing a. Those solutions that are constant functions move together, and all of a sudden they both disappear. And now, as a increases further, you can see all those slope marks have negative slope. If I pick an initial condition here, you'll see the solution curve go down below 0, meaning the fish died off. Okay, you would ignore the part that actually goes below 0. In the lower left corner, you see a graph similar to what I just had up on the other screen. A graph of the right-hand side is a function of p, or in this case y. As I change a, that graph moves up or down. So a bifurcation, a big change has occurred at a certain value of c or a. That's called a bifurcation value. And really, to me, the most interesting thing about Chapter 1 is trying to understand those bifurcations. This is a little preview of that. And that's the end of this video.